Welcome, AP students. We are going to begin in this lesson our Unit 7 review. And this is all about equilibrium. So we're going to be talking about the K values, the unitless K values. K for concentration, K, P for partial pressure. So that's what we're going to be looking at and calculating and understanding K and Q. Hopefully you remember Q as well. So let's get started. So here's a graph. I always like to show graphs. They give us a nice visual representation of what is happening. So when you look at this graph here, you see the rate of the reaction on the one side and the time. And you notice that one starts, so that would be your reactance at the top here. So this line here is representing this, the H2 and the I2. And here you see the actual products beginning to form, and after a certain amount of time, you see the line straightens. Now, that's real important. That straight line does not mean it is static. It is not static. It is dynamic. It is moving in the forward and the reverse direction. So it is in what we call a state of equilibrium, and this is what a graph at equilibrium would look like. So chemical equilibrium, so reversible reactions, a chemical reaction in which the products can react and reform into products and reactants. It goes back and forth, and that's why we have that arrow that goes both ways, like so. That's what that means. So chemical equilibrium, the rate of the forward is equal to the rate of the reverse. So you have no net change. That's the real important part. It's not changing, but there is some going back to products and some forming back to reactants. So it is still in a dynamic state, not static. Please keep that in mind. So equilibrium constant is a number that relates to concentrations of starting material and products of a reversible reaction. So this is given to us. So you don't have to memorize that. If you have your formula sheet, you have a bunch of K values. You have the KC and the KP, and that's what we're going to primarily be looking at. We're not going to be doing the KA, KB, that's the acid base. That section is not on the exam. So you have those provided, and you just have to remember how to use that. So remember, when you look at this, it is the products over the reactants, and the coefficients become the exponents. So it'll be raised to that. So when you look at here, it's big C concentration raised to the coefficient, and the same here, and that is important. And then your reactants obviously on the bottom. So real important to remember, that's how you calculate the K value. So equilibrium constant K is unitless. You heard me mention that earlier. Why is it unitless? Because it cancels out. So the molarity cancels out. Or if you're talking about pressure, the partial pressures cancel out. So real important when you look at that. So here's a little quick example. Calculate the KC equilibrium concentration. So it's telling us here we got some gases. And it says we have some specific moles of these gases, and it tells you right here it is in a container that is 1.00 decimeters cubed. So that's a volume right there. So even though it is a gas, when you're calculating this, you're going to be, if you're giving KC this concentration, you have to have it divided by that. And in this case here, 1, it's going to be the same. But that is your concentration. You plug in those, and this is all 1-to-1. So as you can see here at this point, right here, you just plug these numbers in. You plug the products over the reactants, you plug it in the calculator, and it comes out. In this case, KC is 0.0049, or you could rewrite this as 4.9 times 10 to the 123 negative third. We're going to do several practice problems at the end of this video. So equilibrium law. So when we look at this right here, we are equilibrium constant, and this is talking about concentration, so it's Kc at a given temperature. So remember that if you change the temperature, that affects your equilibrium constant. Also, please remember that a solid does not affect K, and neither does a liquid. So you got to leave off anything that's in the solid state or in the liquid state, unless water would be gaseous, then you'd have to count it. But if it was just water and H2O in the liquid state, it would not go on to your equilibrium equation. It would be left off. And then we have Q, and we're going to talk about Q in a second. So let's talk about K. So please remember K. If K is very small, that means the reaction is favored to the left, which is mostly reactants. So if K is very small, it is reactant favored, so mostly reactants. Intermediate size of a K, that means you're going to have a mix. Significant amount of reactants and products are going to be left. So it may be an equal mix of them. When you talk about a very large K value, 3 or higher, so to speak, now you're going to be product favored. So it's going to be favored mostly to the right, and it will be just a small amount of reactants left. So the larger the number, the less reactants that will be left. So that's really important to remember this, because sometimes you may have something just by looking at the K value determine which way the reaction is going to go, and you've got to be able to remember those few components there. The size is very small, it's reactant favors. It's very large, it's product favored. So reversing the reaction. So if you have given a K value and you're told that the reaction reverse, please make note of this. The reverse reaction is the K value, but 1 divided by the K value. So that's a really important concept. If you're given a K for the forward reaction and it asks what would K value be for the reverse reaction, simply 1 divided by K. So please make a note of that. So if you have a reaction and you multiply it by some number, you must raise K to that number as an exponent. So let's look at an example of what I mean by that. So here we have this reaction, A plus B forms C right here, and we're given a K value. If it said that the reaction was multiplied by a factor of 4, so that means now you have 4A plus 4B reacts to form 4C. You must take K and raise it to the power of 4. Real important. So please make note of that. Now, what is Q? You guys remember Q. K is equilibrium. Q is calculated at any condition. And in most cases, you use Q to find out if, in fact, a reaction is at equilibrium or not. So here we have calculate Q under any condition at any time. And if you notice, it is the same formula, exact same formula. So you don't have to, no other memorization. It's on your, it is given to you on your formula sheet. So remember how I taught you this right here. So draw a number line just like so, and place K on there. It doesn't really matter where you place, and put K. When you calculate Q, if Q is less than K, so if Q ended up being down here, I put a dotted line and put Q right here, that means it's going to go towards K, so it's going to be product favored. If you calculated Q and Q is up here greater than K, I put a dotted line and put Q here. If Q is greater than K, then it's going to be reactant favors and going to move back towards the reactants. Real important to remember that. Now, if Q equals K, the reaction is at equilibrium. So let's talk about the reaction quotient, Q. Measures the relative amount of products and reactants present during a reaction at any particular time in the reaction. And that's why you use it, because you don't know where the reaction is. Is it almost completed? Is it still moving towards product, or is it now moving towards reactant? And that's what you're trying to figure out. That's why you use Q. So K describes equilibrium. So K is all about equilibrium. Q describes a reaction that's not at equilibrium if it doesn't equal K. And then you know which direction the reaction is going to proceed. So here is what I just mentioned about significance of the reaction quotient. If Q equals K, it's equilibrium. If Q is greater than K, it's going to shift back towards the reactants. If Q is less than K, it shifts towards the products. And that's why the number line, I like the number line much better than just putting a greater than an equal sign. Just put a K and then you know which way it's going to go. If Q is greater than K, it's going to go to the left. If Q is less than K, it's going to go to the right. And that number line really helps you view that and see that clearly. So now let's look at some example problems. So that is just a high-level overview of the beginning several sections of Unit 7. So now it's time to jump and get some of these reactions done so we can learn and remember how to utilize these things. Because remember, we will be doing ice tables in this section. All right, so sulfur dioxide reacts with oxygen to produce sulfur trioxide. I don't have a formula, so that's going to be my first thing I'm going to do. So sulfur dioxide, and this is all gases, so I have SO2, and this is a gas. It says reacts with oxygen plus O2, and this is a gas. And this is a reversible reaction here at equilibrium, and it's producing sulfur trioxide. So I have SO3, and that's a gas. Well, I have to balance this right away, and when I look at this here, if I put a 2 here, that gives me 6 oxygens on this side. If I come over here, put a 2, I got 2 sulfur, 4, 5, 6. So I am balanced now. So now let's look at this. It says at equilibrium, partial pressure of each of these is as follows. So it's telling me the partial pressure is at equilibrium, and it wants to know what the Kp value is. So let's write this down. So Kp equals, and it is going to be the partial pressure of SO3 squared divided by the reaction. So now you have the partial pressure of SO2 squared times the pressure partial of oxygen, and that is just 1 there, so I don't need to square that. So now I can plug my numbers in here. So let's get these things written down. So my partial pressure of SO3 is 0.45, and that's going to be squared, divided by SO2 is 0.10 squared, and this is times the partial pressure of oxygen, which is 0.30. So now I get my calculator out and I start to do this process right here. So I can go 0.45 and square that, divided by so when I plug this in, I get 67.5. So 67, so K partial pressure, the equilibrium constant is 67.5, and I only have 2 significant figures on all these, so I can round this off. So that is going to become Kp equals 68. So that is how, in fact, I can do my calculations for this particular example. So hopefully you sort of remember this process of how we've done this. it's important to be able to recollect this. Let's go on to the next problem right here. So I have a water, and I apologize for this arrow. I didn't have a way to write the reversible arrow, so I just put it going back and forth, which gives you the same idea of what's going on here. So my gaseous water is going to go to H2 and it's going to go to O2, and it tells me that my pressure is my Kp is 2.0 times 10 to the negative 42. All right, so it says the initial pressure of H2O is 0.784 atmospheres. What is the partial pressure of each? It wants to know each one. So the first thing I'm going to do is I'm going to write down here, and I'm going to go to H2O, and I have 2H2 plus O2. I'm going to go here. I'm going to go ICE. I'm going to do my ICE table here now. So when I do my ICE table, the initial, it gives it to me right here. So initially I have 0.784. And this is atmospheres, but I'm going to leave the units. I'm just going to do the numbers right now. So here initially I have 0 and I have 0. So at the change is going to be, this is going to be minus 2x, and that's what I have from my coefficient there. And this is going to be plus 2x, and this is going to be plus x. So now at equilibrium, I'm going to have 0.784 minus 2x. I'm going to have 2x, and I'm going to have x. And if you remember, I used to draw the line right there in class when we did this. So now let's write down everything that we're going to be solving for here. So I have Kp equals. So I have H2 squared times O2 divided by H2O, and that's squared. Now I can just plug my numbers into here. So I have here Kp is 2.0 times 10 to the negative 42 equals. And I have 2x squared times x divided by 0.784 minus 2x squared. So if you remember on these type of problems here, when you have this minusing from, and when we look at what x is, we look at the k value is super, super tiny. If I multiplied anything by a number that small and minus it, just think of the significant figures. It is so far down the line that it is irrelevant. So I am just going to get rid of this right here. So I'm going to rewrite this as 2.0x times 10 to the 2.0 times 10 to the negative 42 equals, and I'm going to have up here 2x cubed divided by 0.784 squared. All right, so now I am going to take that 0.784 and multiply it. So I'm going to do this all at one time. I'm going to cross multiply here. So I'm going to multiply this by that. I'm going to divide it by the 2. I'm going to do it all in the calculator at one shot. Divide it by 2, and then I'm going to take the cube root of it. So let's get that done. So I'm going to go 0.784 squared. And I'm going to multiply that by 2.0 times 10 to the negative 42. I'm going to divide that by 2, and then I'm going to take that number and take the cube root of it. And I should come up with, let's see here, 6.7. I got 2 sig figs, 6.7 times 10 to the negative 15. So x equals 6.7 times 10 to the negative 15. So that's what I have come up to with x. So now let's get the partial pressures of each of these. So O2, and O2 is just x, as you can see here. So O2 is 6.7 times 10 to the negative 15 atmospheres. H2 equals, and it's 2 times x. So I'm going to multiply that, and 6.7 e to the negative 15 times 2. So I'm going to get 1.3 times 10 to the negative 14 atmospheres. And then now I'm going to get 0.784 minus 1.3 to the 14. And you can see that that really didn't affect it much at all. So the H2O is going to still be 0.784 atmospheres. So here is my final answer. All right, so we broke out the ice table first time in a while, so hopefully you remember the process that we just did. Now let's look at our next problem here. So here we've got a reaction going to take place, and it says the partial pressures, of SO2, O2, and SO3 are as follows. So it gives us all these things here, and it wants to know if this reaction is at equilibrium, and it gives us. So what are we solving for here? We are solving for Q. So the first thing I do is write my reaction. So I have SO2 plus O2 is going to form SO3. I've got to balance this, so I'm going to put a 2 here and put a 2 here. And that's all I need to do. So when I'm going to calculate Q, so I'm going to put my number line right down here like I taught you to do. I got my number line here, and I'm going to come up here. I'm going to put K equals 86.1. I'm just going to write that there. So now let's calculate Q. So Q equals, and in this case here, it is going to be SO3 squared divided by SO2 squared times O2. So now let me plug in, and this is respectable as far as how it is all written out here. So I have 1.28 squared divided by my SO2 is 0.286 squared, and my O2 is 0.414, and that's going to equal Q. So now let me get my calculator going here. So I got 1.28 squared divided by 0.286 squared times 0.414, and close my parentheses. And it comes out to, let's see, 3 sig figs I need. So 48.4. So Q equals 48.4. All right, now I know right away this is not at equilibrium. So I'm going to take my line and I'm going to plot it. And I'm going to put Q over here, 48.4. So by placing that, this reaction is going to be product favored. So it is going to proceed to the left, and it is going to favor product. So the formation of SO3. And that is my answer for this particular question right here. All right, so now let's do this last one. This one's a little bit more of a complex problem, so let's go ahead and get started on this one. So I have a reaction here, and it gives me the mass of each of the things that are placed in this empty vessel. So the first thing I want to do is I'm going to come over here. I'm going to write it over here on the side. I'm going to go H2 plus Br2, and that's going to equal HBr. And each of those is squared, so I'm going to have to put a 2 in the front of that, so that now balance it out. Okay, so now when I look at this here, I have been given 2.5, so let me come over here and write this down. So I have 2.523 grams of H2. I'm going to come right below it. I'm going to go 200 grams, 200.0 grams of Br2. And I got to go to moles right away. So 1 mole of H2 is 2.02 grams of H2. And this here is going to be in, and it tells me right here, it's a 0.450 milliliter vessel. That is in liters is going to be 0.450 liters. So that can get my concentration right away there. So I have 2.523 divided by 2.02, and then I'm going to divide that by 0.450, and that is going to be equal to 2.78. So 2.78, and I'll put a capital M, and that is H2. So now the Br2 here. So let me go right away, do the same thing, and go to moles here. So 1 mole of Br2. And I don't know what the molar mass is, so I'm going to have to get my periodic table out here real quick. And I have 79.90. I get 159.8. 159.80 grams. And once again, this is in the same size container, 0.450 liters. So let me plug this into my calculator. So I have 200 divided by 159.80, and I'm going to divide that by 0.450. So I'm going to have 2.78 as well. So 2.78 molar Br2. So now the next thing I'm going to do is I'm going to do my ice table, because I've gotten to a point where I know what my initials are. This is my initial concentration. So now I have to proceed forward. So I'm just going to put a line down through here just like that to separate. So I have ICE, my ice table. So my initial concentrations here is 2.78. This is 2.78, and this is 0. There's nothing there. So initially at the change, this is going to be minus X, this is going to be minus X, and this is going to be plus 2X. So at equilibrium, this is 2.78 minus X. This is 2.78 minus X, and this is 2X. So now I can go ahead and set up my equation here. So I have my Kc equals, and I'm going to plug in the, I'm going to have H, B, R, and this is going to be squared divided by concentration of H2 times the concentration of Br2. So I am trying to find out equilibrium concentration of HBr of the product. So now I can plug in this information, which is going to help me derive that. So my Kc, it gave it to me as 400. So I'm going to go like this. So this is 400 equals, and HBr is 2x, and I'm going to go squared divided by, and when I look at what's happening here, I'm going to have 2.78 minus x squared. All right. So what I'm going to do here is, because I have a square on both sides, I can do this. So what I'm going to do is I'm going to take the square root of this side and the square root of this side. So the square root of 400, so let me jot this down. Square root of 400 is 20. So I'm going to have 20 equals, and I'm going to have 2x over 2.78 minus x. All right, so now I can multiply both sides here. So I'm going to go 20 times 2.78 is 20 times, 2.78, and that's 55.6. So I'm going to have 55.6, and I'm going to have minus 20x equals 2x. All right, so now I'm going to add both sides. So I'm going to go to isolate my variable, so plus 20x, and I'm going to have 22x equals 55.6. So now I'm going to divide by x, and I'm going to divide by 22. That isolates my x, divide by 22. So that's going to mean x equals. So I divide both sides by x. X cancels off here, leaving my, 22 cancels, leaving my x. So I have 55.6 divided by 22. So I have 2.53. So x equals 2.53. So I've solved for x now. So now let's make some sense of this. So it's asking for the concentration of HBr. So HBr is 2 times x. So the concentration of HBr equals 2x. Well, I solve for x. So this is going to be 2 times 2.53. So now if I do that, 2.53 times 2 is 5.06. So the concentration of HBr is going to be 5.06 molar. So that's using an ice table to calculate the concentration of a product. So we've done a couple ice tables. We've done a Q variable. Hopefully, a lot of this hopefully comes back. I will have a lot more problems. We've done 4 problems tonight on this lesson. That's the last one that I have for you today. I will have more on Monday. There is a AP Classroom quiz that's due on Monday at 11:45 p.m. So please look at working on that over the weekend. Try the example problems from Monday's virtual lesson, and then you should be able to complete that AP Classroom without any problem. All right, I appreciate you watching. Thank you. Go in peace.